guys are doing well. I'm doing quite okay. It's now Easter Monday, so I've had a free day. Let's see, where did we end up last time? We did until problem 17b. And 17c, if you recall, was something I just didn't know how to do. But hey, let's now hop into problem number 18. And let's see if we can solve it. See if we can solve it. See if we can solve it. Suppose that b squared minus 4c is greater than or equal to 0. Show that the numbers ching 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 and ching 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 both satisfy the equation x squared plus bx plus c is equal to 0. Well, when I was doing this, before this video, I just kind of skipped a part because I already knew how to do them. How to complete the square with the whole thing. So I just straight up did that. Like but I guess we can quickly do 18a, which means just plugging these in. But maybe that isn't that interesting. No, I don't think it is that interesting, so maybe we just hop onto B immediately. Suppose that b squared minus 4c is less than 0. Show that there are no numbers x satisfying x squared plus bx plus c is equal to 0. Hint, complete the square. So let's complete the square. 18b. So b squared minus 4c is less than 0. And then we have the equation x squared plus bx plus c equal to 0 plus c plus c plus c. And then let's complete the square. So we get x plus b over 2 squared plus c minus b squared over 4 is equal to 0. And so we get that multiplying by 4 and moving these two to the other side, we get that 4 times x plus b over 2 squared is equal to b squared minus 4c. And well, the left side is a square times the constant, also a square by the way. So it's always greater than or equal to 0, but the right hand side is less than 0, and thus no solutions for this equation. Quite simple, 0, then x squared plus xy plus y squared is greater than 0. Okay. So, if x and y are not both 0, so let's make the assumption that without, if you aren't familiar with this, this means without loss of generality. Meaning, and we imply by this that we make some assumption which trivially doesn't loses any generality of the proof. So without loss of generality, assume that at least y is not equal to 0. And okay, we have this equation x squared plus xy plus y squared. And we can think of x as the x and of y as like the constants a and b, for example. And thus what I mean by this, that in this case b is equal to y and c is equal to y squared, you know. And thus b squared minus 4c is equal to y squared minus 4y squared equal to negative 3y squared. Which is obviously, because y squared is always positive, so this is obviously less than 0. And well, this means that, well, in our terms, b squared minus 4c is now less than 0. And as we found out in b, if b squared minus 4c is less than 0, this implies that x squared plus bx plus c is greater than 0. Now I realize that I didn't exactly show that part, but it follows quite clearly from completing the square. Because well, if we assumed here that it's less than or equal to 0, then this would also trivially be false, and thus it clearly implies this straight away. By just completing the square, we find this fact. And then, because in our definition of b and c, or yeah, we found that b squared minus 4c in this kind of quadratic equation was less than 0. Thus, we find that x squared plus xy plus y squared is greater than 0. Nice. Then d, for which numbers alpha is it true that x squared plus alpha xy plus y squared is greater than 0 whenever x and y are not both 0? How would you approach this problem? this as a function of x, where alpha and y, we can think of them as b and c. And thus we get that b in terms of the again things discussed previously is now equal to alpha y, and c is equal to y squared. Thus b squared minus 4c is equal to alpha squared y minus 4y squared. And well, we want to find when this is greater than 0, and thus we want b squared minus 4c be less than 0. So alpha squared, oh this is b squared, y squared minus 4y squared less than 0. So y squared times alpha squared minus 4 less than 0. And because y squared is always positive, we want is alpha squared minus 4 be less than 0. And how do we get this? Well, then alpha squared is less than 4, and thus alpha is less than 2 and greater than minus 2. So whenever alpha is between minus 2 and 2, this expression is greater than 0. Then E. Find the smallest possible value of x squared plus bx plus c and ax squared plus bx plus c for a greater than 0. And well, again just completing the square, and because this is a subcase of this, we'll just do this, which is the famous quadratic equation. And many of you are probably familiar with the formula for the solutions of the quadratic equation, and usually the proof just is done through completing the square, and we'll now do the same thing. So 18e, we have ax squared plus bx plus c. And this is equal to, well, a times x squared plus c. And thus we want to find the minimum of this, which occurs when this expression is 0. So this is the minimum. Yeah, quite simple. Look at my jewelry. Yeah. So the minimum is b squared over 4a plus c plus c. Now let's move on to problem 19, which is about the Schwarz inequality, called the great granddaddy of all inequalities. I'll drink quickly, but you can already look at problem A. Problem A is asking us to prove that if x1 is equal to lambda y1 and x2 is equal to lambda y2 for some positive number lambda, then the equality holds in the Schwarz inequality. So let's do that first. So 19a, the left hand side is equal to x1 y1 plus x2 y2. And if x1 is equal to lambda y1 and x2 is equal to lambda y2, then this is equal to lambda y1 squared plus lambda y2 squared. But then the right hand side is equal to square root of x1 squared plus x2 squared times square root of y1 squared plus y2 squared. So it's square root of x1 squared plus x2 squared times square root of y1 squared plus y2 squared is equal to, again using the lambda definitions, lambda squared y1 squared plus lambda squared x2 squared times, no, y2 squared, sorry, plus y1 squared plus y2 squared is equal to lambda times y1 squared plus y2 squared, because we just multiply two similar square roots together to get that thing inside it, which is equal to lambda y1 squared plus lambda y2 squared, which is equal to left hand side. So the equality holds approaches 0. But now suppose that y1 and y2 are not both 0. And that there is no I'll move you a bit. Number lambda such that x1 is equal to lambda y1 and x2 is equal to lambda y2. Then this chain of inequalities, this chain of logic holds true. Using problem 18, complete the proof of Schwarz inequality. And you may ask, what was problem 18? And I answer you, it was the previous problem. So this should be fresh in your minds right now. And well, just by looking at this, we can see that it looks very much like some kind of quadratic expression in terms of lambda, which is greater than 0. And the fact that it's greater than 0 means that b squared minus 4ac must be less than 0. So b squared minus 4 ac less than 0. Meaning that b squared is less than 4ac, of course. And well, the b in here is negative 2 pum 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 x1 y1 plus x2 y2. Now we square this, and that is less than 4 times ac. Now I need to start a new row here. Like this. Then let's just take the square root. And obviously this minus sign goes away because this is squared. So we take the square root 2 times x1 y1 plus x2 y2 is less than square root of 4 is 2. So 2 times square root of y1 squared plus y2 squared times square root of x1 squared plus x2 squared, and it already looks quite familiar. And obviously just by dividing it by 2 we find the Schwarz inequality. And so this is a very nice way of proving it. This kind of obvious chain of inequalities, and then just using facts from problem 18 to find a pretty and easy proof for the Schwarz inequality. I won't bother writing down again, but I did it on my practice paper, and I'll just show my solution here. I hope you understand it. So if you're interested, just look at this. But I think the basic idea is quite clear again here. But it's just so much writing, and I'm in a bit of a hurry now. I want to finish problem 19. And, well, part C. Prove the Schwarz inequality by first proving this equality. And, well, this is just mechanical algebraic calculation or computing, so if you want to do it, I'll leave it to you, but I'll not do it here. But how can the Schwarz inequality be proven from this? What do you think? I'm actually not completely sure, so we can try to find the solution together. Obviously, the left hand side is just the right hand side of the Schwarz inequality without the square root signs. So somehow we need to combine these two expressions so that this is kind of staying here, because it has the things we want, that is x1 y1 plus x2 y2. Oh yeah, obviously. Because, well, this is obviously positive because it's a square, so this whole sum is obviously greater than just having this, and so we have that c x1 squared plus x2 squared times y1 squared plus y2 squared is equal to x1 y1 plus x2 y2 squared plus x1 y2 minus x2 y1 squared, which is greater than or equal to just this part, x1 y1 plus x2 y2 squared. And this is true because this is always greater than or equal to 0. And then we just take the square root to get the desired result. Sorry, I zoned out for a second. But one thing I'm left to wonder, I'm taking the square root, but it should kind of be plus or minus. Oh yeah, but it doesn't because it's an inequality. So it just double flips. If that makes sense. You know, like for example, if a is, let's say a squared greater than or equal to 4, then, well, a greater than or equal to 2, or a less than or equal to minus 2, times minus 1, a greater than or equal to 2, and we arrive at the same conclusion. That's why the taking the square root isn't a problem. That's why I was wondering it a bit and being a bit unsure. But that is why I think. And when, well, there's also part D, which you can do at home, deduce from each of these proofs that equality holds only when y's are 0 or when there is a number lambda, such that x1 is equal to lambda y1 and x2 is equal to lambda y2. So sure, if you're interested, do that at home. But unfortunately, I have to end this video now because I have to get back to the barracks. Back to the barracks. And still, chapter 1 remains not fully done, which I'm a bit annoyed at. I'm annoyed at myself. But maths, you must give mathematics its time, and if the problems take more time, then they take more time, and we just have to deal with that. And I think it's much more important to give the problems the time they need and the attention they deserve, rather than hurrying quickly forward. I mean, this project might take several years, but I might finish it. So yeah, I hope you enjoyed this quick